A warm welcome to part 3 of the lecture on functions. In the previous lecture, we looked at quite a few examples of some of the standard functions. In this lecture, we intend to formalize an important notion, that of the graph of the function. Many of you would probably think of the graph of a function in terms of some smooth curves or sketches drawn on the xy plane like a straight line or a parabola, etc. While all that is intimately related to the graph of a function, strictly speaking, it is not exactly how the graph of a function is mathematically defined. So we shall proceed to give a formal mathematical definition of the graph of the function. In that direction, let us first introduce the concept of Cartesian product of sets. Let A and B be two sets. The Cartesian product of the sets A and B is another set denoted by A cross B and is defined in the following way. A cross B is the collection of all points of the form small a comma b such that small a belongs to the set A and small b belongs to the set capital B. A typical point in the Cartesian product, which is of the form a comma b, is called an ordered pair. Therefore, the Cartesian product is the collection of all ordered pairs a comma b. The Cartesian product of n sets a1, a2 all the way up to an is defined likewise. a1 cross a2 cross a3 cross up to an is defined as the collection of all points of the form a1, a2, a3, up to an such that each ai belongs to the set capital AI, where I goes from 1, 2, 3 up to n. Consider the xy plane. We know that the xy plane is nothing but the collection of points of the form x, y, where each of the coordinates x and y belongs to the set of real numbers. But this is nothing but the Cartesian product of R with itself as per our definition. So the conclusion is that our familiar xy plane is basically the Cartesian product of the set R with itself. R cross R, for the sake of brevity, is written as R2 rather than R cross R. So the xy plane is nothing but R2. We now proceed to give a formal definition of the graph of a function. Let f be a function from R to R. The graph of f is a subset of R2 or the xy plane defined as follows. Graph of f is defined as the collection of all points x, y such that x belongs to R and y is equal to f of x. Let us consider some examples. Consider the constant function fx equal to c. As per our definition, the graph of f is the collection of points of the form x, c, where x belongs to R. The graph of f can be represented on the xy plane by means of this straight line y equal to c, because the graph of f has the y coordinate fixed at c. Consider another example, the identity function fx equal to x. The graph of f is the collection of points in the xy plane of the form x, x, where x belongs to R. The plot of the graph in this case happens to be the straight line y equal to x. Consider fx equal to x square. The graph of f will be the collection of points of the form x, x square, where x belongs to R. And the plot of the graph on the xy plane will be our standard parabola y equal to x square. Similarly, let us consider the exponential function fx equal to e to the power x. The graph of this function will look like this, as shown. Consider the logarithmic function fx equal to ln x, where x is strictly greater than 0. The graph of f is the collection of points of the form x, ln x such that x is greater than 0. The graph of the logarithmic function has this form as shown in the figure. The graph of the sine function is the collection of points of the form x comma sine x, where x belongs to R, and when plotted on the xy plane, the graph of sine x has this familiar form. Consider now the greatest integer function, fx equal to square bracket of x. The graph of f will be the collection of points of the form x comma square bracket of x such that x belongs to R. The graph of the greatest integer function has this particular form. These open circles indicate that that particular endpoint is not included in a particular segment. Similarly, for the least integer function, the plot of the graph looks like this. There is an important remark which I need to make. There do exist functions whose graph cannot be plotted. For example, consider the function fx equal to 1 if x is a rational number and 0 if x is an irrational number. The graph of f will consist of points of the form x comma f of x such that x belongs to R. I urge you to try and plot the graph of this function. And let me know if you meet with any success in the comment section. We now proceed to give a classification of functions based on different parameters or conditions. The first among which will be the classification based on the domain and range of the function. If the range of the function is R or C, or a subset of R or C, the function is called a real or complex valued function. In other words, if the function takes values in the real number line or the complex plane, we say that the function is real valued or complex valued depending upon the case. For example, consider the function fx equal to x square plus 1. Now, x square plus 1 is a real number for every x belonging to R. So this function f is a real valued function. Similarly, the function fx equal to x plus ix square is a complex valued function because it takes values in the set of complex numbers. If the range of the function is a subset of Rn or Cn, the function is said to be a vector valued function. We will encounter these type of functions during our study of vector calculus in greater detail. As an example, consider fx equal to x comma 2x. Here, the function takes values in R2. Therefore, this is an example of a vector valued function. And so is the other function fx equal to x comma x square comma x3, which belongs to R3. This function f takes values in R3. Hence, this is also a valid example of a vector valued function. If the domain of the function is R or C or a subset of it, the function f is said to be a function of a single real or complex variable. For example, consider fx equal to x plus e to the power x, where x belongs to R. Here the domain of the function is the set R. Therefore, the function is said to be a function of a single real variable. As another example, consider f of z equal to z square plus 1, where z belongs to C. This is an example of a function of a single complex variable. If the domain of the function is Rn or Cn, n greater than or equal to 2, or a subset of Rn or Cn, the function is said to be a function of several real or complex variables depending upon the case. For example, consider the function f of x comma y equal to x square plus y square. So this is an example of a function of several real variables. Moreover, since the function takes values in the set of real numbers, it is also an example of a real valued function of several real variables. Similarly, f of x comma y comma z equal to xy comma yz comma zx is an example of a vector valued function of several real variables. Finally, let us consider the function f of z1, z2 equal to z1, z2. This is an example of a complex valued function of several complex variables as per our definition. Vector calculus is the study of vector valued or real valued functions of several real variables. We will study these functions in much greater detail a little later in the course. I will stop at this point, and in the next lecture we will continue with our classification of functions. Thank you.